Hi, this is the video for Further Maths Year 2, and we're looking at non-homogeneous second order differential equations. So the way this works is you find the solution for the homogeneous differential equation, and then you find what you need to add on, because remember, the homogeneous differential equation gets you to 0. I'll show you with an example. Let's look at this equation. So we can see now we're used to solving differential equations that are equal to 0. This is non-homogeneous. This is not equal to 0. This is equal to 3. So the way to do this is to solve the homogeneous differential equation. That gets us to 0. And then think about, what do I need to add on to get us to 3? And there's a lot of terminology here and a lot of use of language which we do need to know, but we already know the maths. The auxiliary equation, oops, pen broke. The auxiliary equation is m squared minus 5m plus 6 equals 0. Straightforward enough. Minus 3 minus 2. And so the complementary function we'll call it YCF is AE to the 3x plus BE to the 2x. That's where we got before. So the things to do is consider the homogeneous equation, set it equal to 0, solve as we did before. Okay, so I've got a function in y that will get my right hand side to 0, but I need to add on something else to get it to 3. Now, in this case, it's fairly obvious what we add on. What I need is a function where you differentiate it and you differentiate it again and you sub in and you end up with this constant. And if we think about it, we'll come to the conclusion that my right hand side, if it's a constant, it will differentiate to 0 and it will differentiate again to 0, so it should be fairly straightforward. I'm just going to use my common sense. It's called the particular integral. What function of y do I need to try that when I sub in I get 3? I'm going to try some constant alpha. So I differentiate, of course I get 0, differentiate it again. Oops, did that the other day, didn't I? And then if I sub into the original equation, I get 0 minus 5 lots of 0 plus 6 alpha is 3. So alpha is a half. That means that my particular integral is half. Okay, another learning point. The general solution to my second order differential equation is the complementary function plus the particular integral. The general solution is the complementary function plus the particular integral. So y is AE to the 3x plus BE to the 2x plus a half. That's the general solution to this differential equation, and it's general because I still haven't found values of a and b. And of course, just like I do with linear equations, non-differential ones, I need values to sub in to find a and b, and that's the next section. So in this case, because the right hand side was a constant, I just assumed y, the particular interval, would be some constant. Okay, I'm going to do the same equation again, well, the same left-hand side. D squared y dx squared minus 5 dy dx plus 6y equals, and this time the right hand side is now a function of x. Now this is less straightforward because of course I'm going to assume it's some multiple of x, but when you differentiate it, it doesn't go to 0. So I need to find what function can I get for y where when I differentiate again it fits this. Again, I already know the complementary function. I don't need to do this again. A to the 3x plus b e to the 2x. I don't need to go through that rigmarole again. It's exactly the same as it was before. But for the particular integral, I'm now going to try a linear function of x. And don't forget, that includes a constant. So alpha x plus beta. So dy dx is not x, is alpha. Second derivative is 0. Sub into the original equation, 0 minus 5 alpha plus 6 alpha x plus beta equals 2x. Simplify that. In fact, I can't really simplify it, can I? What I'm going to do is I'm going to compare coefficients. Compare coefficients of x. Well, 6 alpha equals 2. So alpha is a third. And I also know if I compare my constants, I've got minus 5 alpha plus 6 beta is 0. So minus 5 over 3 plus 6 beta is 0. Beta's what? 5 over 18. So my particular integral then is a third x plus 5 over 18, which means my general solution is my complementary function plus my particular integral. Okay, same left hand side. But now my right hand side is a quadratic. Again, complementary function is the same. For the particular integral, I'm going to attempt a quadratic. So I get alpha x squared plus beta x plus gamma. Dy dx is 2 alpha x plus beta. Second derivative is 2 alpha. Substitute into my original equation, so 2 alpha minus 5 times 2 alpha x plus beta plus 6 times alpha x squared plus beta x plus gamma equals 3x squared. Compare my coefficients of x squared. 6 alpha is 3. So alpha is a half. Compare my coefficients of x. What have I got? 10 alpha plus 6 beta is 0. I know my alpha. Minus 10 alpha, sorry. Good. So beta equals 5/6. And then if I compare my constants, 2 alpha minus 5 beta plus 6 gamma equals 0. That gives me gamma is 19/36. So my particular integral then is half x squared plus 5/6 of x plus 19/36. So the general solution is complementary function plus particular integral. So depending on the right hand side, I need to pick a particular integral that fits. And that's the skill here. Now the A-level spec only requires a subset of particular integrals, so it's not any function in x. I'm going to do another one. Same equation on same left hand side again. So I don't need to go through the beginning steps. I already know this. I'm going to try a multiple of e to the x. Well, we can see straight away it's going to work, isn't it? Sub into the original equation, alpha e to the x minus 5 alpha e to the x plus 6 alpha e to the x. So 6 plus 1, 7 take away 5, so 2 alpha e to the x equals e to the x, which means 2 alpha is 1, alpha is a half. So the particular integral is half e to the x, and my general solution is complementary function plus particular integral. I just want to say again, the reason that my general solution is the complementary function plus a particular integral is because, remember, the complementary function is the function of y that gets us to 0, and then adding on the particular integral gives me what I need on the right hand side. One more with this particular equation. Complementary function as before. Now I'm looking at my particular integral being a trig function. Now remember, sine differentiates to cos and cos differentiates to minus sine. So I actually need, for my particular integral, I need a sine term and a cos term. So I'm going to go for alpha sine 3x plus beta cos 3x. And it's important that I recognise whatever my particular integral is trig, it has to have a sine term and a cos term. dy dx, sine differentiates to cos, so 3 alpha sine 3x. No, that's not true. 3 alpha cos 3x, sorry. Cos differentiates to minus sine, so minus 3 beta sine 3x. Differentiate again. Cos differentiates to minus sine, so minus 9 alpha sine 3x. Sine differentiates to cos of minus 9 beta cos 3x. Substitute into my original equation, minus 9 alpha sine 3x minus 9 beta cos 3x minus 5 lots of dy dx, so minus 15 alpha cos 3x plus 15 beta sine 3x plus 6 lots of y plus 6 alpha sine 3x plus 6 beta cos 3x, and that all equals 13 sine 3x. So I'm going to compare coefficients of sine 3x. In fact, I'll factorise first. On the left hand side, my sine 3x terms, what I've got, minus 9 alpha plus 15 beta plus 6 alpha. So minus 9 alpha plus 6 alpha, that's minus 3 alpha, that's a cos, plus 15 beta. And my cos terms, I suspect I've done this wrongly. I might pause it in a second, check. My cos terms, minus 9 beta minus 15 alpha plus 6 beta. Let's see what happens. So that equals 13 sine 3x. That means that minus 3 alpha plus 15 beta is 13, and minus 9 beta plus 6 beta minus 3 beta minus 15 alpha is 0. Hopefully this works and I get alpha equals minus a sixth and beta equals 5/6. So my particular integral then is minus a sixth sine 3x plus 5/6 cos 3x, and my general solution is complementary function plus, I'll put my plus there so I'll do it this way, plus particular integral. So like I say, the skill here is picking the form of my particular integral, and the A-level spec only covers these cases. If my right hand side is constant, then the particular integral, try constant. If it's a multiple of x, try a function of x. If it's quadratic, try quadratic, not forgetting that there's an x squared term, a linear term, and a constant. If it's an exponential, try the exponential. If it's a trig, try a trig. Now remember, it could be just a sine term or just a cos term, but that just means a or b is equal to 0. But if it was just sine or just cos, you still need a sine and a cos term because they differentiate to give the other function. So if we can work out what particular integral to try, it's not ridiculously hard. Now, of course, it just gets harder. Look at this example. Same left-hand side. Which means the complementary function is the same, a e to the 3x plus b e to the 2x. Now for the particular integral, I can't just try alpha e to the 2x. That's what the table says to do. Try alpha e to the 2x. But I've already got an alpha e to the 2x term in my complementary function. So it's already been used, if you like, by the complementary function. There's no point in adding another e to the 2x term, because I know already that's going to take it to 0. Because this has already been used, so I can't use alpha e to the 2x. It does work though if I multiply this term by x. So if my particular integral that I want to try appears in the complementary function, I need to multiply by x, and it does work. So let's differentiate. Well, this would be the chain rule, the product rule. So u is alpha x, u dash is alpha, v is e to the 2x, v dash is 2e to the 2x, so it's going to be u dash v alpha e to the 2x plus uv dash 2 alpha x e to the 2x. Differentiate again. 2 alpha e to the 2x, and this is just alpha x e to the 2x, which I've already differentiated, doubled, so it's 2 lots of dy dx. So 2 alpha e to the 2x plus 4 alpha x e to the 2x. Let's simplify that. And if I sub these into the original equation, we'll see that it works. I know you can't see the left-hand side, but I'm copying it out correctly. So 4 alpha e to the 2x plus 4 alpha x e to the 2x minus 5 lots of alpha e to the 2x plus 2 alpha x e to the 2x plus 6 lots of alpha x e to the 2x. Let's see what happens. 4 alpha e to the 2x minus 5 alpha e to the 2x plus 6 alpha e to the 2x. That gives me 5 alpha e to the 2x. Just check that yet. 10 minus 5. So 5 alpha e to the 2x. 4 alpha x e to the 2x. Sorry, that's not correct, is it? 4 alpha x e to the 2x minus 10 alpha x e to the 2x plus 6 alpha x e to the 2x is 0. Good. And then I've got 4 alpha e to the 2x minus 5 alpha e to the 2x. So let me do that again. 4 alpha e to the 2x minus 5 alpha e to the 2x. So that's minus alpha e to the 2x. I've got 4 alpha x e to the 2x minus 10 alpha x e to the 2x plus 6 alpha x e to the 2x. That's 0, so it works. And on the right hand side it's e to the 2x, so alpha is minus 1. That means that my particular integral is minus x e to the 2x, and my general solution is my complementary function plus my particular integral. So given the table, if y pi is part of the complementary function multiplied by x. And if x, y, pi, multiplied by x squared. Okay, have a go at 7c. For the rest of today. I think also on Friday's lesson we'll carry on with 7c. I hope that makes sense. Okay, let me know if you need anything. Bye-bye.